start. Welcome to the second talk of this session about distributed machine learning with the Samsara DSL of the Apache Mahou project. Before we start, let me quickly introduce myself. I'm Sebastian. I'm at the moment finishing my PhD on scaling data mining and massively parallel data flow systems with TU Berlin here. And I'm working as a machine learning scientist and postdoctoral researcher with the Berlin-based machine learning group of Amazon for 2/3 of a week. And in my remaining time, I'm now a senior researcher at the database group of TU Berlin. And I work on the intersection between databases and machine learning. Besides that, I'm also a member of the Apache Software Foundation, where I worked on Mahou, Giraffe, and Flink. And similar to the previous speaker, I'm a bit inactive at the moment. I hope this changes in the future. Now, this talk is about Samsara. And in summary, Samsara is an easy-to-use, domain-specific language for distributed large-scale machine learning on systems like Apache Spark and Apache Flink. And it's part of the Apache Mahou project. That sounds very complicated, but actually Samsara is very easy to use, and it tries to solve a big problem. And the big problem nowadays is that a lot of people want to do large-scale data analysis on large data sets, and then naturally they have to do this on platforms like Apache Flink or Apache Spark. But if you program these platforms, then you have to have some kind of understanding of how they work. So data is partitioned, some operations trigger repartitioning and network communication. So it's very easy to do something wrong and to produce programs that either run very slow or that are hard to read. And the ideal environment would be something that looks like R or MATLAB, which people who have a background in statistics or mathematics are familiar with, but automatically runs in parallel on these systems. And this is what Samsara tries to provide to you. So you get a programming and scripting environment based on Scala. And the idea is that you have a DSL that is on the one hand system agnostic, so you can run it on many parallel systems, and that allows you to program in a way that is very close to the actual math of the algorithms that you're implementing. So I have an example here. You see there's this complicated formula that involves outer products between vectors and subtractions and a matrix multiplication and so on. And this is something that you would find in a textbook if you look up an algorithm. Now the nice thing is that this line below, which says val G is, and then this piece of Scala code, is actually the Samsara implementation of this line of code. So that's Scala, and it's basically just typing down the formula with some operators that look a bit different from the math. So this %* is the operator for matrix multiplication. If you've used R, then you're probably familiar with that. And that is everything that you as a user need to provide to the system in order to compute this formula up there on a parallel system like Flink or Spark. Because what Samsara is doing is it's taking this piece of code, it's pushing it through a so-called algebraic expression optimizer, so something that is a bit similar to what compilers or databases do. And then it translates this automatically to distributed engines like Flink or Spark and executes this in parallel. So that is the high-level picture. The things that you get with Samsara are pretty similar to what you know from, let's say, MATLAB or R. So there are Scala real values. There are two types of in-memory vectors, like dense vectors, sparse vectors, optimized for random access or for fast reading. You have in-memory matrices, sparse and dense matrices, and also a number of specialized matrices, like diagonal matrices. And up till that, it's pretty much just a Scala DSL that looks like R, for example. But Samsara has one special thing, which in my eyes is very elegant, and that is the so-called distributed row matrix, DRM. And that is a huge matrix that is partitioned by its rows, and that's living in the cluster. It's stored in the main memory of the cluster. And the nice thing is that you can also do operations on this distributed row matrix, but you can only do a subset of the operations that you can do on an in-memory matrix, on a distributed row matrix. And that is by intention, because a lot of the operations that you can do if your matrix is in memory and you have random access are very, very hard to scale. So this distributed matrix only offers you the operations that are easy to scale. So that that helps programmers helps to prevent programmers from writing hard to parallelize code. And a lot of these operations on the distributed row matrices are special, and we will see some examples later. You also get the typical things, so you can multiply matrices, you can transpose them, you can combine in-memory matrices and matrices that live in the cluster. You can slice out stuff from matrices. You can also do assignments, but you can only do assignments to in-memory matrices because as soon as we would provide random access to distributed matrices, this would also be dangerous because it's sometimes very hard to scale if you can't predict the access pattern. And you have support for cross products and dot products and standard summaries. Furthermore, there's some machinery for working with matrices, the usual stuff. So there's a solver for linear systems. There's a set of the most common in-memory decompositions, like eigendecomposition or SVD. There's even a few distributed decompositions that work on the large matrices that live in the cluster, like a specialized QR decomposition or a stochastic SVD. And you can also hint the system a little bit by telling it to cache and checkpoint certain matrices if you want to do a sequence of operations on that. And I think the easiest way to get a feeling for this Samsara DSL is to simply look at an example. So we'll do a very simple example. You shouldn't put this into production. There's also a lot of things that I'm leaving out here, but it's just so that you get some kind of feeling of how this works. So in this example, we have a very small data set of cereals. And for every cereal, we have a few numbers that show the weight of some kind of ingredient, like protein, fat, carbohydrates, and sugars. And we have some customer rating that somehow denotes how much the customers like this type of cereal. And what we're trying to do is we're trying to implement linear regression. So we're basically trying to predict this customer rating from the weights of the ingredients. So linear regression is a standard technique. I'm sure most of you have heard of this. So we have this target variable y, the customer rating, and we assume that it's generated by a linear combination of these features, which are the weights that live in some matrix X. And we are trying to estimate a parameter vector that tells us how much these actual features contribute to the rating. And geometrically, it means we have some points in space, and we're trying to fit a line to these points. Now, the first thing that you would do if you would use Samsara to approach this use case is you would load your data set as a distributed row matrix from the distributed file system. So it would look like this. There is this DRM from HDFS command. In this example, we just mimic this. So we use this DRM parallelize command that just lets us take an in-memory matrix and put it into the cluster. So we start with that matrix that represents our data set. Now, the first thing that we need to do is we need to prepare the data a little. So we said the target variable y, which is a vector, is the customer rating. And the weights of the ingredients are the features that live in a matrix X. So from this large matrix that holds all our data, we first slice out X. So we basically take the 4 first columns, so that that science means take all the rows and then the 4 first columns. And we also put the last column into a vector. Just 2 lines of code. The next thing that we need to do is we need to find some way to estimate this parameter vector. Now, the simplest way, the textbook way, is to use ordinary least squares. So we want to minimize the sum of residual squares between the true target variable and our prediction of the target variable. And the nice thing is that there's a closed form expression for this. So if we compute this this formula that you see there, we get an estimate of this parameter vector. And I've already showed this to you in the beginning. If you have some linear algebra formulas, that is pretty easy to implement in Samsara. So if we wanted to start doing this, at first we need to compute x transpose x, that's the left part of this formula, and x transpose y, the right part of this formula. So we can just type that in. So we say our variable drmxtx is simply the drmx transposed times drmx. And the same thing goes for the variable drmxty. So it's basically just typing down the formulas. Now, if we have those, we need to solve the following linear system, and then we get this estimate of beta. In this case, we'll take a very, very simple approach, because we simply take the result of x transpose x and the result of x transpose y and fetch it into the memory of the driver machine. And then we use an in-core solver on the driver machine. This is based on the assumption that x transpose x actually fits into the memory of the driver. So that is something that you have to guarantee for this use case. But the good thing is that x transpose x is actually has a size that is the columns of x times the columns of x. So if you have a small set of features, this xtx is very small, even if you have like millions of observations. And we can be sure that it fits into memory. So in code, that boils down to just these 3 lines. So we call collect on this drmxtx. That means fetch the matrix from the cluster into the memory of the driver. And we also call collect on the result of drmxty. And we give it a parameter that we just want 1 column vector so that the system knows that xty is actually a vector. And then we can just use this in-memory linear system solver, which is just a solve function, analogous to R, and we get an estimate of this parameter vector. And that's it. So it's just a few lines of code, and we've implemented a distributed linear regression that we can now run on Spark or Flink. And we can play more with it. So basically, most things that you can do with linear algebra are super easy in Samsara. So we can now look at the prediction that we get from our model. So that is just multiplying the matrix by this parameter, by this estimate of the parameter vector. And then we could look at the difference between the real customer ratings and the one that we predicted to somehow see how well our model worked. And we could now even go on and refine this implementation of it, because at the moment it's just a toy implementation. So in a real use case, you would add a lot of things. So one thing that you would, for example, add is a bias term that is like a constant factor that's always added to the model that shifts that line. And one trick that people use is to simply add a column of 1s to the feature matrix, and then basically the model will learn a bias term that is simply the weight for this column of 1s. Just a common trick that you can look up. Now I think nowadays Samsara even has support for that, so there's like an operator that you can call. But when I created this tutorial, there was no support for it, and I'm using this to showcase some advanced features of Samsara. So the cool thing is that Samsara, because it's running in this distributed world, can offer you a bit more things than something like MATLAB or R give you out of the box. So Samsara gives you, for a distributed row matrix, this map block function that allows you to write some user code in Scala, so basically arbitrary code, and do custom modifications to these large matrices that live in the cluster. So in our case, we can use this map block method to simply add a column of 1s to this matrix. So we would take our feature matrix X, invoke this map block method. So we give it a hint that the result will have an additional column, because the internal optimizer needs to keep track of the size of the matrices. And then we simply write a Scala function. So the input are the keys of a certain part of a matrix and the block. So it's basically just some part of the matrix with the keys, which can be, I think, ints or strings. And then we would create a block that looks like the actual block that we see, but with 1 additional column. We would copy the old data into this new block and make the last column of this internal block just consist of 1s. And then we return this. So with that, we can easily use user-defined functions to do complicated things on matrices that live in the main memory. And that would be it. And I think other features are also very, very simple to implement in Samsara. But the really interesting stuff is actually the stuff that you don't see when you program this. So the idea here is really to make it super easy to program, make it look like R, and have the system do the optimization and heavy lifting under the covers. At the moment, the systems that are supported are Spark, so there's a prototype for that. There's also a prototype for H2O, but I haven't tried this yet. And we are at the moment actively working on support for Apache Flink. So there's a big pull request that is currently in the making, and I think it should be in the next weeks. So the good thing here is really you write your program in this abstract language that looks like R or MATLAB, and then you can pick one of these systems and simply run it there. And if you're not happy with one of them, you can switch to another one. And the thing that Samsara is doing internally is it executes these programs and optimizes them. So what you want to have in an ideal world is something what databases give you for decades already. So if you do a query to a database, you don't tell the database how to execute your query. You just declaratively tell it what you want. So you say, please join these two tables on this key and then group the result. And you put this query to the database and you let the database figure out how to do this. So databases have several ways of executing joins or aggregations, and the database has an internal optimizer that will then try to find the optimal way of executing this query. And Samsara is trying to do a step in this direction for these MATLAB-like programs. So you as a user provide something like a declarative formulation of your program. You just say A transpose A, for example, and then the system should figure out what's the best way to execute this matrix multiplication. And this works as follows. So the first thing to understand is that the actual execution of operations on the distributed matrices is deferred. So if you write matrix C is A transpose times A, actually you're just composing logical operators. So the system will remember what you're doing, but will not execute this at the moment. And then there are some things that we call computational actions that implicitly trigger the optimization and execution of your program. So usually that's things that require you to materialize the data. So if you say write some matrix to the file system, you obviously have to compute it at that point in time. And also if you fetch the result of some computation into the main memory of the driver, you also have to compute it. So you write some code, the system remembers this code, and then if you use one of these actions, the system will trigger the optimization and then execute your program on a parallel system. I think the optimizer is still very much in its infancy, but it already takes a few optimization factors into account, like the size of the operands, the orientation of the matrix, and so on. And there's already a few operators implemented for matrix multiplication, and this is something that people can improve. So for any system, you can add more operators for matrix multiplication, for example, and people wouldn't need to change their programs. And we look at a specific matrix multiplication, and I will show you how the system would optimize and execute this actual computation. So we take this A transpose A. In our example, it was X transpose times X, and that is something that you see in a lot of programs, because it basically just means comparing columns in a matrix. And if you have this piece of user code, the question is, how should the system optimally execute this? Now, the naive way would be to simply execute it as you see it. So you would do two passes over the data. In the first pass, you would transpose this matrix A. Depending on the representation, that probably requires you to repartition A. So if A lives in a matrix and you transpose it, so you change rows and columns, then in many cases the machines need to send data over the network, you need to reshuffle the data set. So in that case, that already cost us like one complete transfer of the data set. And then in a second step, we would need to multiply the result of the transposition of A with the original A. So that would require a distributed matrix multiplication, and which is usually very expensive and would probably require us to repartition the data again. So we need to send at least two copies of the data set over the network. That is very costly. Now, what Samsara does here is it has a special operator for this kind of matrix multiplication, because it's a very common special case. And it would use pattern matching on this logical graph, so on this logical plan. So Samsara keeps track of the operations that you want to execute. So it would see this and would find a pattern here and would then internally replace this plan by a very simple plan that just uses its transpose times self operator, which is an optimized implementation for this kind of computation. So that is a very simple optimization on the logical level that Samsara would apply. The mathematical approach which Samsara takes for this transpose times self style matrix multiplications rely on the so-called row outer product formulation of matrix multiplications. So there are many ways to do matrix multiplications, and depending on how your data looks like and how it's partitioned, one of the other might be better. Now, the trick that we're using here is that if you look at A transpose A, you can basically take every row of A, compute the outer product of the row with itself, and sum up all the results. That also gives you A transpose A. And the nice thing is that if you think about this in a parallel or MapReduce-like way, if your matrix is already partitioned by the rows, then you can execute this computation in a single pass over the data. So in MapReduce, you would every mapper would take a row, compute the outer product, emit the result, and then the reducers would sum that up. So graphically, it looks like this. So let's say this is our matrix A. And we actually want to compute this product, but we never have to explicitly materialize A transpose. And what we're doing is we're taking the first row, computing the outer product with itself, adding to that the second row, and so on and so on. And that also gives you the correct result. And again, the nice thing is that you as a user don't have to think about this. This is something that would happen under the covers. You don't need to know that. You just write this one line of code. So that is on the. So we're now moving to basically the physical level. And similar to databases, Samsara has several physical operators. So for example, a database typically can do hash joins or submerge joins, and then the optimizer somehow has to find out what join to use for a given query. And that is also true for Samsara. So Samsara has two physical operators for this transpose times self operation. One is like the standard operator that always works. And then another operator, which is called 88 slim, that is a specialized implementation for tall and skinny matrices, like the one that we saw in this linear regression example. So for matrices that only have a few columns, but can have many, many rows. And we will see how you can exploit this. Now, the optimizer must have some way of choosing between these implementations. Ideally, you would want this decision to be cost-based, depending on estimates of intermediate result sizes or something. At the moment, it's done very simple, so there's just some threshold that you can define. But again, there is a lot of potential for improving this implementation, and users wouldn't have to change their programs. And so in the last slides of this talk, I'm going to walk you through an example how these operators actually look like in a distributed system. So let's take a very simple example. We have this matrix A, 4 columns, 3 rows. And it's a distributed matrix that is partitioned over 2 machines, so over worker 1 and worker 2. Worker 1 has the first 2 rows of A, and worker 2 has the third row of A. Now, the first thing which this operator determines is the number of output partitions. I think the easiest, the typical case is to say, okay, we have 2 input partitions. Let's also pick two output partitions. And now we need to compute the intermediate results for these 2 output partitions. So what we do is actually an advanced version of this row outer product formulation of matrix multiplication. So we start with computing the results for the first partition. So we take the rightmost half of every vector and compute the outer product with the vector. We do this for the first row in parallel, and we also do it for the second row here. And now in the next step, we compute the intermediate results for the second partition. So here we do the same thing, but we use the rightmost half instead of the leftmost half. So again here, half of the vector, outer product with the vector. We do this in parallel for both of them. We compute the intermediate results. And now the only thing that is left is to sum them up using a distributed aggregation. So that is a very, very simple algorithm that runs in basically 1 map and 1 reduce step that allows you to efficiently conduct this matrix multiplication in parallel. And the nice thing is that it also allows us to compute the memory, to control the memory a little bit, because we can control how much of the vector we take, and we could also, this could also be like an out-of-core implementation or an implementation that can work with constrained memory. And in the end, we have the result A transpose A, which has 4 rows and 4 columns, and it's partitioned over these 2 workers. So that was A transpose A. This operator A transpose A slim works in a similar way with some optimizations. So again, we have this matrix A, which is partitioned over 2 machines. Worker 1 has the first 2 rows, worker 2 has the second 2 rows. And now we assume that we can keep the intermediate results, or matrix of size columns times columns of A, in memory. That is some assumption that so the system will believe you. If it doesn't work, it will crash. But if you know this from your data, like if you know that you have only very few features, then you can safely execute that program. And now in that case, this operator would first do 2 matrix multiplications internally on the machines. So A1 transpose A1 and A2 transpose A2. And to save some memory, it only computes the upper half of that, because the resulting matrices are symmetric. And then we can just take these matrices. I think at the moment Samsara fetches them on the driver, because if they're small, we can do that, and sums them up on the driver. And again, you have the result. Yeah. And that's it. And remember, the heavy lifting is done internally in the system, and you as a user hopefully don't really have to care about this. Yeah, that already closes the talk. So if you're interested in the Flink part of that, there's the ticket Mahout 1570, which has pointers to the Flink implementation, and which should also lead you to the pull request that we're currently reviewing. And if you would like to learn more about this system, Apache Mahout has extensive documentation on Samsara, which you find under these URLs. And also, you can also approach me and ask questions. So I was probably a bit fast, but thank you for listening, and feel free to ask me questions if you want. Yeah.
I had a question. It's very interesting. First, nice talk.
Thank you.
About the DSL part, you said you put your own domain knowledge into the optimization of the workflow. So how do you prevent that Flink, for example, or Spark, the system that actually executes the workflow, doesn't destroy your optimization?
So the optimizer is not independent of the system. So if you implement like the runtime for a specific system, you should also implement the optimizer that is specific for this system, because it also depends on the system what you need to do. So I think in Spark you need to do a few more things, because Spark is more rudimentary, but Flink also has its own optimizer, so you can probably, we haven't done much experimentation on that, but you can probably leverage a lot of that in the runtime.
Are
No, it's done via the dataset API. Yeah.
I have a question concerning this distributed row matrices. I mean, is there also a notion of distributed row vectors? Because matrix multiplication is basically matrix vector multiplication and then sorts it. And in your example of linear regression, you have to also do this X transpose Y. So in other applications like Krylov substrate methods, you have several matrix vector multiplications with the same that follow the same distribution structure. So is there, or do I have to code this as distributed row matrix as well?
Yeah, I think at the moment, unfortunately, the vector is just a matrix with one row or one column.
So I can code it as distributed row matrix
Yep.
as well?
Yep. No more questions? Okay. Thank you, and I think we have an early start for the lunch.